Hi, this is going to be test prep for ENGPHYS 3004, test number 9. In 2018, we're going to look at the 2017 test number 9. This test covers the introduction to how to calculate the convection coefficient for different kinds of flow. So first it looks at the external flow stuff. So the first question is, for flow around a cylinder, Nusselt number as a function of theta exhibits either one or two local minima. Explain what's happening at each of the minima and why Nusselt number at theta is decreasing with theta when theta is lower than the minima. Okay, so this is referring to, if we go over to the topic summaries in chapter 19, this thing from section 19.4 in the textbook. So this is a plot of what the Nusselt number is at a bunch of different Reynolds numbers for flow around a cylinder as a function of angle from the stagnation point, which is right at the front of the cylinder. So what's happening as you move around and increase the angle is you're increasing the boundary layer of that flow. You're increasing the thickness of the boundary layer, and that means that the temperature difference is between the surface and the edge of the thermal boundary layer is over a larger distance, which means that the temperature gradient that happens right at the surface, other things equal, is going to be lower, and therefore you're not going to have as high of a convection coefficient and not as high of a Nusselt number. As you move around the object, that boundary layer increases in thickness, and then you end up with a again, lower temperature gradient because of that increase in temperature thickness. But eventually what happens is you have flow separation, and that leads to increased mixing, which makes up for the fact that the total boundary layer thickness is larger. You've got extra mixing, which is moving away heat right at the surface in that wake region, even in laminar flow there. Now what happens here is at the point where you would start forming a wake region in laminar, instead what happens at these Reynolds numbers is the flow trips into turbulence, and that drastically increases the Nusselt number from this transition to turbulence at this set of Reynolds number. And so once you're in turbulence, you've got a lot more mixing anyway. It also delays the flow separation, so that part happens a little bit later over here. So to answer the question of what's happening at each of the minima, the first minima here is the flow is separating. Here the flow was about to separate, but then it switches into turbulence. And here is where the flow actually separates for turbulence. The second question, why does nu as a function of theta decrease with theta when theta is lower than the minima? That's because the boundary layer is expanding. So again, as we move, say here, when we're lower than the minima, why does it decrease with theta? That's because we got an increasing boundary layer. Here, why does it decrease with theta there? Increasing boundary layer thickness. Okay, next question. Suppose for some system, experimentation shows the local Nusselt number at a specific velocity and set of fluid properties is given by this, x squared, for x is in the set of 0 to L, where x is in meters. So really this would have to be dimensionless. Calculate the global Nusselt number for the section from 0 to L. So presumably there's some kind of a scaling in here. Don't worry about that. Okay, what we know is that the local Nusselt number is related to the local convection coefficient multiplied by whatever distance length we're at, so whatever characteristic length. So in this case, over some plate, we'd use x, and then we're going to divide that by the conductivity of that surface. Whereas the global Nusselt number is based on the global h times the total length over k. Now, it's not actually that the global Nusselt number is the average of the local Nusselt number, but rather the h in the global Nusselt number is the average of the h in the of the local h, which is the one in the local Nusselt number. So first we have to take this and figure out what hx is. So hx is Nusselt number times k over x, and then you can average this to figure out h is equal to average of hx with respect to x. So in other words, you integrate it from 0 to L and then divide that by L. And then we can find the global Nusselt number through HL over K. So if you like, we could do this sort of one at a time or kind of substitute one thing into the next thing. Why don't we go ahead and do it that way? So h as a function of x, substituting in the Nusselt number of x squared would equal x times k. And then after we put that into here, xk dx, we're going to have that it's 1 over L times L squared k over 2. So that's going to be equal to L times k. And then after we substitute that back in for h, we're going to have that we have L squared over 2. So yeah, okay. What we've got, just to look things over, we've got that the local Nusselt number being x squared allowed us to figure out what the local convection coefficient was, just x times k, as you move along this plate maybe. Then the global convection coefficient is the average of the local convection coefficient. So that would be L times k over, whoops, dropped something there, L times k over 2. Then the global Nusselt number is the one based on the local, the average convection coefficient. So substituting in Lk over 2, we end up with just L squared over 2. Next question. For flow over a flat plate at a uniform temperature, sketch the hydrodynamic and thermal boundary layers if the Prandtl number is 2, up to a max of 2 times the critical length. So Prandtl number is defined as the ratio of the molecular diffusivity of momentum to the molecular diffusivity of heat, so nu over alpha. And because of that, it tells you the relative thickness of the boundary layer. If the Prandtl number is bigger than 1, then the momentum boundary layer is thicker, and if Prandtl number is less than 1, then the thermal boundary layer is thicker, because this thing on the denominator, the thermal diffusivity, must be larger. Okay, so let's grab a picture of the boundary layers. The boundary layer for momentum is maybe in this picture. Then what we can do is paste that over in Paint. And we've got one boundary layer there. This is the momentum boundary layer. So let's draw on a thermal boundary layer. I'm going to use some magic wand selection here and then paste that and shrink it down. So because we have a smaller thickness by about a factor of 2, maybe the thermal boundary layer would look just like the momentum one, but down by a factor of 2. If the Prandtl number was less than 1, then we'd have this actually be higher. If it was equal to 1, you'd expect them to coincide, but it's going to be lower as long as you have a Prandtl number that is bigger than 1. And when it's about 2, then maybe it'd be about this low. So let's zoom in and maybe see if we can do that. Change around the thickness of that tolerance to paint in our boundary layer there. Nope. Okay. More or less all nice and thermally. So there we go. Thermal boundary layer drawn on alongside the momentum boundary layer. Final question. In a certain reactor, pressurized liquid water with a free stream velocity of 8 meters per second and free stream temperature of 20 degrees C flows around a 4 centimeter diameter cylinder with a circular cross section. The surface of the cylinder is at a uniform surface temperature of 300 degrees C. Calculate the average convection coefficient and the rate of heat transfer per 1 meter length of the cylinder. So to do this, we're going to be figuring out the Reynolds number. Find the Reynolds number. Then we're going to find the Nusselt number. Maybe we'll also figure out we're going to get some parameters. So maybe the 0th step would be get parameters, which we're probably going to need what? We're going to need the kinematic viscosity. we're going to need the Prandtl number and anything else that we're going to need. Well, we'll come back to that. Probably the conductivity for water, for the fluid. Okay, so yeah, that would be the kinematic viscosity and Prandtl number for the fluid as well. Just, yeah. Next part. Once we've got the Nusselt number, then we can use that to figure out the convection coefficient. Use Nusselt number is equal to h diameter over k to find h. So that's the average Nusselt number for the whole thing that we're going to need to figure out. Yeah, and then we can figure out the rate of heat transfer for 1 meter length of the cylinder. Use Q dot is equal to h Ts minus T infinity times the area to figure that out, to find the rate of heat transfer. For the area is equal to pi diameter times the length, 1 meters. 1 meter. Okay. So at this point, we're ready to explain what the rest of these parameters are. So the kinematic viscosity is nu, which is equal to the dynamic viscosity over the density. So we got that. The Prandtl number we'll just have in a table. We can look up both of these parameters in a table at the back of the book. The conductivity for water, which is K. We're going to have to look up all of these at the film temperature. And why do we know that? Well, that's because of the equation that we're going to use for the Nusselt number. So the Nusselt number equation we want is the Churchill-Bernstein equation. And this is for the total Nusselt number around a cylinder. And that's this really long equation. It works as long as the Reynolds number times the Prandtl number is greater than 0.2. And this is going to be for the Nusselt number to find the average convection coefficient around a cylinder. The Reynolds number that we're going to be dealing with, Reynolds number is Reynolds number for a cylinder, which is equal to the velocity times the diameter divided by the kinematic viscosity. After we figured that out, then we should be good to go for that parameter. Okay, so let's see. We've got some things that we can put in right away. So we've got the velocity, which is 8. We've got the diameter is 0.04. We've got the surface temperature, which is 300, and the free stream temperature, which is 20 degrees. So from the average of those, we can find the film temperature, and averaging those should give us 160 Ts plus T inf over 2. So there we go, 160 is the film temperature, and that's what we're going to use to look up the other parameters that we need. So the parameters that we're going to need nu based on mu over rho. We're going to need to figure out what mu and rho are. And we're going to need to figure out what K is for later. So that should be, oh, and the Prandtl number. Yeah, so we can get all of these things in the back of the textbook. So here is the instructor resource for the appendix, and we've got this. This is the same as the one that you have printed in your copy of the textbook. So table A15 has all these useful properties of water. At 160, the film temperature, we can figure out what the we can get all the information that we need. So the density is 907. Why don't we temporarily put this here? You have to be really careful to read off of the right column. So mu is equal to the dynamic viscosity for the liquid, 0.17 E minus 3. The density, 907.4. The conductivity is for the liquid 0.68. And the Prandtl number, again for the liquid, 1.09. Very common spot to make a mistake. So let's check 0.17 E minus 3 for the dynamic viscosity, 907.4 for the density, 0.68 for the thermal conductivity, and the Prandtl number 1.09. And we're doing all of this for liquid water at the film temperature that we have. All right. So with these, with this setup, we can move on to the next part of things, which is to calculate what the Reynolds number would be, and that's velocity times the diameter divided by nu, and we find a Reynolds number of 1.7 million. So we're definitely good for the Reynolds number times the Prandtl number check to be able to use this. Something just slightly higher because the Prandtl number is only about 9% higher than 1. So 9% increase on the Reynolds number, still above 0.2. Okay, so then we need the Nusselt number. The Nusselt number for the cylinder here is equal to 0.3 plus, and this is another source of error, typing this equation in incorrectly. 0.62 times Reynolds number to the power of 0.5 times Prandtl number to the power of 1/3. It's forced floating point evaluation, and we're going to take all of that and divide by this thing in the denominator, 1 plus 0.4 divided by the Prandtl number, all to the power of 2.0/3, and then we're going to take that to the power of 0.25. Then that whole thing is multiplied by 1 plus the Reynolds number divided by 282,000, and that's to the power of 5.0/8 to the power of 0.8. Okay, so that should be the Nusselt number if we haven't made any mistakes in typing out that formula, or in your case entering that formula into the calculator, also a source of error. Then once you've got that, we can figure out what the H would be by saying H would be Nusselt number times K divided by the diameter. So we get 39,000 for the convection coefficient, quite high. And then we can take that and multiply. Q dot is equal to H times Ts minus T infinity times the surface area, which is pi times the diameter times a length, which is 1. Okay, so we've got a rate of heat transfer of 1.39 megawatts. And that's it. Hope that helps. I'll see you next time.